Somebody sent me. Yeah, he's having trouble.
I sent it to him twice, so he should.
Yeah, so make sure you come back. Yeah. Yeah.
Six, three.
Hi.
Yes.
What? This hasn't ever spent. So, Studios. She's a champ. She's lost. Yes. She's it's been multiple fellowships, which is science at multiple offices and she was St. President Honor Society and for my education. Since graduation, largest accomplishments while she was here. That was my first a couple more arguments left to be had to decide on which figures are going to be the final judge.
Not that you did. I am here.
Oh, man. Thank you for such a lovely introduction, Ava. Really appreciate it. It has been an honor to be the first graduate student in your lab, and I'm really grateful that you put me on really exciting projects and have been so thoughtful and intentional about building me into being the best scientist. To my friends and family who've traveled far and wide to be here, thank you for coming today. Folks on Zoom, I know I have folks here in Belgium, it's like 8 p.m. there, so thank you for logging in today, I appreciate it.
I don't think the sound is coming through Zoom.
Oh.
I just got a text about it.
Okay.
It is now. We got it.
All right, good. And I'm really excited to share the work that I've been doing in the lab for the past few years. And in Dave's lab, we study the cardiac ion channel hERG, which is a major regulator of heart function. And my projects have focused on its role as a potential antiarrhythmic therapy, as well as its role in early development. So first, I'll just give an outline of what I'm going to discuss today. Just giving a general overview of cardiac function, as well as HERG1's role in cardiac physiology. And then I'll move into the structure and function of HERG1 and its biophysical properties. And then move into discussing my 2 data chapters, one focusing on HERG1 as an antiarrhythmic drug target for long QT syndrome, and then as well as how different isoforms of HERG1 can mediate ICAR sensitivity to acidosis. So heart disease is the leading cause of death globally, worldwide. And within the subset of that includes cardiac arrhythmia, which is also a leading cause of death. And arrhythmia is essentially when your heart is beating out of sync or irregularly. And that is a consequence of electrical dysfunction. And so arrhythmia can ultimately lead to the onset of sudden cardiac death, which affects over 300,000 people each year. And our lab is specifically interested in studying long QT syndrome, which increases the risk for arrhythmia and thereby sudden cardiac death. And so one of my projects focused on addressing an unmet need for therapies that focus on treating and restoring disrupted cardiac function, as opposed to just focusing on treating the symptoms of disease. And so the heart's function generally is just to pump blood throughout the body. And that's coordinated by an electrical system. So your atria will contract and pump blood into the ventricles, and then your ventricle contracts and pumps blood out to the rest of your body. And so we can use an electrocardiogram or an ECG as a tool to assess heart function. And it's essentially a composite reporting of action potentials that are produced in the heart, which is illustrated here on the slide. And so the cardiac conduction system is ultimately responsible for coordinating contraction in the heart. And it begins with an electrical impulse that starts at the sinoatrial node. It continues down to the atrioventricular node, through to the bundle of His, splits at the left and right bundle branches, and continues through to the Purkinje fibers, through to the ventricles. And so this propagation of this electrical impulse through the heart is what we refer to as an action potential. And an action potential is ultimately the electrical signal that's responsible for coordinating contraction. So here's an example of a standard ECG or electrocardiogram, and I'm highlighting 5 major waves here, consisting of the P, Q, R, S, and T waves. So the P wave is indicative of atrial depolarization. The QRS complex is indicative of ventricular depolarization, and the T wave is indicative of ventricular depolarization. And so one of the hallmarks of cardiac arrhythmia is a prolonged action potential duration. So here I'm illustrating an example of a healthy ventricular action potential and corresponding ECG of the QT interval. And here below is an example of prolonged action potential duration as a consequence of disrupted ventricular function. And so that's reflected by a prolongation of the QT interval on a standard ECG, hence the name of the syndrome that our studies, long QT syndrome. And that increases the risk for arrhythmia. And here's an example of Torsades de Pointes, which is essentially a ventricular tachycardia, means your ventricles are beating too quickly and ineffective at pumping blood out to the rest of the body. And that subsequently can promote the onset of sudden cardiac death. And so a healthy ventricular action potential consists of a number of depolarizing and repolarizing currents illustrated here. And I want to focus your attention on IKR, which is one of the major outward repolarizing potassium currents that's responsible for phase 3 repolarization of your cardiac action potential. And HERG1, which is the ion channel that our lab studies, is responsible for conducting FKR. So one of the questions we asked is, are there ways for us to modulate HERG1 function such that we can increase this outward repolarizing current in the context of diseases that are characterized by a prolonged action potential duration to restore normal, healthy cardiac repolarization and prevent the onset of arrhythmia and sudden cardiac death? And so why does anybody care about HERG1? What's so special about it? So off-target HERG1 block ultimately leads to prolongation of the action potential duration, increasing the risk for arrhythmia and sudden cardiac death. And it's actually a major liability in the pharmaceutical industry. And so in this table below, I'm just highlighting a number of drugs in the 90s and early 2000s that were pulled off the market because they were later found to have off-target pharmacological HERG1 block and increase the risk for arrhythmia and sudden cardiac death. So as a consequence, now any lead compounds that are in development to become any kind of therapeutic have to be screened against HERG toxicity to ensure that they're not having some sort of unintended off-target HERG1 block. You can imagine you don't want to put a medication on the market that's going to cause you to die. So now that I've talked a little bit about cardiac function and the importance of HERG1's role, I'm going to focus on talking more about the structure and function and some important properties of the channel. So HERG1 is a voltage-gated tetrameric potassium channel, and I'm highlighting the major domains here in these colors. Here's a cryo-EM structure solved by Rod McKinnon's lab of the HERG1 channel. And so in orange, you have an N-terminal cytosolic regulatory PAS domain that interacts with the C-terminal cyclic nucleotide binding homology domain highlighted here in aqua and regulates channel gating. You also have helical transmembrane segments shown here in yellow and green. Segments 1 through 4 comprise the voltage sensor domain, which detect changes in memory potential. Segments 5 through 6 comprise the pore domain through which your potassium ions flow. And so an interesting and unique feature about HERG1 channels is that they're very slow to activate, which means they go from a closed to an open conducting state very slowly, but they also rapidly inactivate, meaning they go from this open conducting state to this inactivated non-conducting state very quickly. And so we can see that if we measure HERG1 or record HERG1 current from hex cells that are stably expressed in HERG1. So an example of that is illustrated below, where we have a voltage protocol where we hold cells at a voltage where HERG channels are closed. As we step to positive potential, HERG channels begin to activate and conduct current. But because they rapidly inactivate, HERG current is suppressed during this portion of the step pulse. As you step down to potentials where now HERG channels are able to recover from an activation and come out of that inactivated state, you get what we refer to as a tail current, which is a release of the HERG1 current that was suppressed in the prior step pulse. And then we see ultimately that current hit. And so we can see the same phenomena if we use a voltage protocol that mimics the ventricular action potential. So again, starting at potentials where channels are closed and non-conducting, as you depolarize, you see the onset of HERG1 current, but it's suppressed quickly due to the rapid onset of inactivation. And then as we begin to repolarize cells, they're able to recover from inactivation. And again, you see this onset of channel current and then decay as the channels begin to close. And so there are two isoforms or two different subunits of HERG1 that combine to form a functioning channel. We have the HERG1A subunit, which I highlighted earlier in the cryo-EM structure. And then we have the HERG1B subunit, which is identical to HERG1A, except that it does not have this PAS domain in its N-terminus, and it has a shorter and a unique N-terminus with about 36 amino acids. And so an important feature about this PAS domain is that its presence actually slows HERG1 gating or closing of the channel. And so that's illustrated here, where you can record the time course of deactivation in either homomeric 1A channels or heteromeric channels expressing both 1A and 1B subunits. And you can see here that the time course of deactivation is much faster in the heteromeric channels compared to the homomeric channels. And when we see this shift in accelerated deactivation, we also observed a twofold increase in the onset of activation. So channels are opening more quickly and connecting more current. And we also see a twofold increase in recovery from an activation. So although the channels are closing more quickly, because they're also activating and recovering from an activation, the net effect is that heteromeric channels conduct more HERG1 current compared to homomeric channels, which is illustrated here. So shifting HERG1 subunit abundance, the relative abundance of 1A or 1B, it can be proarrhythmic. So there was a group that showed that you can express the PAS domain by itself with the HERG1B subunit, and the PAS domain will associate with that N-terminal region of HERG1B and ultimately convert it into a HERG1A like channel. So it has properties that are essentially indistinguishable from a HERG1A subunit. And so here they're showing that if you express the PAS domain, it causes a prolongation of the action potential duration, the onset of early after depolarizations, which are illustrated here, which is essentially when the action potential begins to repolarize, you have an early depolarization event that leads to triggered activity. And it also increases variability. And these are the hallmarks of proarrhythmia at the single cell level. So now that I've talked a bit about the structure and function and role of HERG1 in cardiac physiology, it's going to the exciting part and introduce some background information so we can talk about the studies I've done in the lab. So there are several groups that have investigated the use of HERG1 activators as potential therapeutics for long QT syndrome and other diseases of disruptive cardiac repolarization. And here I'm just highlighting a few. There are a lot of HERG1 activators that have been developed and several that have been tested across different animal models. But the main gist of this is that they either cause ventricular fibrillation in some of the models that were tested. They could either overcorrect for action potential duration and ultimately lead to short QT syndrome, which is also proarrhythmic, or kind of a mixture of all of these events. And so one thing I want to highlight here is that ventricular fibrillation is the most lethal form of arrhythmia. Your ventricles are pretty much fluttering, unable to contract, and they're not ejecting any kind, they're not delivering any kind of blood from them. So there was a study that was done where they tested a HERG1 activator, NS1643, in a rabbit model for long QT syndrome type 1. And long QT syndrome type 1 occurs when either IKS current is blocked or completely abolished. And this is the other repolarizing current that's important for phase 3 repolarization. So diminishing this current also leads to a prolonged action potential duration and increases the risk for arrhythmia. So the idea here was to introduce this HERG1 activator, perhaps it could compensate for the loss of IKS and thereby restore corrected cardiac repolarization. So they found that NS1643 was indeed able to shorten the QT interval compared to vehicle controls, which is wonderful news. And they also found that NS1643 significantly shortened the action potential duration, which is also great news. But they also found that this HERG1 activator increased the incidence for ventricular fibrillation. So that's not a great side effect for an antiarrhythmic therapeutic. So several years after this, a study came out where they identified that a number of HERG1 or small molecules that were deemed HERG1 selective activators were actually not selective for HERG1 alone. So here I'm showing examples of HERG1, BK, or TRK2 core domain channels. And the traces in color, so an orange, brown, and pink, show what the currents look like when each one of these channels are activated. In this study, they tested this small molecule illustrated here on BK and TRK2 core domain channels and found that and found that third time's the charm, that this small molecule also activated PK and shut portable channels. So clearly it is not selected for the hERG channel. And so they identified a novel pharmacophore that they call the negatively charged activating pharmacophore, which is shown here. And these are the 3 small molecules that they tested in the study, showing that they do share this pharmacophore that was responsible for activating all the channels. So I want you to focus your attention on NS353. This is a structural analog of NS1643, which is used in that non-PC1 model. So perhaps one possibility is that some of the off-target arrhythmic effects may have been a consequence of the small molecule that they thought was hERG unselected is also hitting other applications. So now I'm going to move into my first data chapter where we investigated the use of a PAS targeting HERG1 activator as an antiarrhythmic in an image model for lung. So our collaborators at the University of Porto developed a single chamber fragment antibody, or SCFP, as a tool to modulate and study HERG1 behavior. And so it consists of a variable heavy and variable light chain that are connected by a short loop. And this SCFP binds within the first 10 residues of the PAS domain, and it disrupts its interaction between the C-terminal cyclic nucleotide molecule domain. And so they found that when you record HERG1 current from hex cells that are stably expressing HERG, and you intracellularly perfuse purified SCFP, it actually shifts and accelerates the time course of deactivation. So that's shown here, quantified here to the right. So showing sample traces from recordings of deactivation, and you can fit a bi-exponential equation to this curve and extract the time constant to reflect how quickly the channel is moving. So the smaller time constant for SCFP are reflective of the fact that the channel path of faster gating. And so I mentioned earlier that if you see this accelerated gating phenotype, as you can see with the heteromeric 1A channels, you also see an increase in HERG1 current. So essentially what they found was expressing this SCFP on 1A channels essentially converted them, or they more mimics a 1A, 1B like heteromeric channel, such that we saw faster deactivation as well as increased current. And so they tested this now in stem cell derived cardiomyocytes to see if it would translate from a heterologous system. And so indeed, when they used the whole protocol and the molecular action potential, they saw that the SCFP did increase IKR in stem cell derived cardiomyocytes. And given an increase in IKR that outwardly polarizing current, you'd expect to see a shortening of the action potential duration when expecting these SCFPs, and that's indeed what they saw. So just to summarize what I've described thus far, we know that disabling the PAS domain using this SCFP ultimately increases IKR and has the ability to shorten action and filtration. And this suggests that this is a rationale for possibly developing PAS targeting therapeutics to treat diseases that are associated with prolonged action potential duration. And so we hypothesized that perhaps SCFP expression could be therapeutic in a model of lung disease. So to test this, we used patient-derived stem cell cardiomyocytes that came from either a healthy donor or from a patient that had Dravet-Lengnielsen syndrome. And Dravet-Lengnielsen syndrome is a severe form of wonky T-centered type 1, where IKS is completely abolished due to mutation that introduces the stop codon and then complete deletion of exon 3. And so no protein is produced, no RNA is produced, and the current should not be present. And so as a consequence, the cell line is highly pro-arrhythmic. And so we work with the vector group here at the University of Michigan, where we subclone DNA, encoding the SCFP into a lentiviral compatible vector, and then they essentially developed lentiviral particles that we use to transfuse in the SCFP only to sample particles. And so we predicted that SCFP expression should produce markers of arrhythmia in this shale environment. And so the idea here being that we transduce J1s and record these pro-markers of arrhythmia, including action potential duration, where we would expect SVP to shorten the action potential duration, action potential variability, as well as the onset of early active equalizations. So we expect AP shortening, reduction in variability, and less onset of early active equalizations. And at the single cell level, early active equalizations or PADs are essentially how arrhythmias manifest. And so first we had to validate the JLN line to ensure that ITS would be absent, that the cells were pro-arrhythmic compared to control cells. And so we took focal images of JLN cardiomyocytes that were immunolabeled either for KCNQ1 protein, so the protein that's responsible for conducting ITS, labeled for actin using colloidin or with DAPI. And then we quantified the mean fluorescence intensity, which is shown here to the right. And so you can see in the image, but as well as in the quantification, that KCNQ1 expression is essentially. So I also reported ITS current from both of these from control and JLN cardiomyocytes, and indeed saw that ITS current was effectively absent in the genomic background. So then we also repeated the confocal experiment, this time doing the labeling for HERG1 to ensure that our target is being expressed, which is the excitation. And here is the quantification against the right. And interestingly, we see that HERG1 expression is significantly reduced in the JLN line, which I will come back to in these slides. And one point I want to make here is that there are a few studies that can show or suggest that KCNQ1 and HERG1 interact with their C-terminal domains. So if you knock down KCNQ1, you also knock down HERG1. Mutations in KCNQ1 have also been shown to disrupt HERG1 trafficking to the membrane. And so this supports, work that's been shown in prior studies. So then I also reported spontaneous action potentials for control or JLN lines and measured the action potential duration at 90% repolarization. And as expected, we saw that JLN cardiomyocytes had a prolonged AE. So now that we've validated the JLN line, I then went in to record IPM current. So here I'm showing sample traces from sample trace recordings from JLN cardiomyocytes that were transduced either with GAP or with SVP, which has the shaping. And then the patch cells that were corrected and record IPRs equal to sensitive current. And so here I'm showing graphs of steady state current density as well as cell current density. Steady state, we measured the current at the end of this step that I'm highlighting here, normalized to the capacitance of the cell or across the side of the cell. And then tail current density is what I explained earlier, that tail current that's elicited at the depth of the potential of the tail from recovered from an activation, that maximum tail current normalized to the capacitance as well. We can see here, we saw that there was a significant increase in steady state current density, as well as tail current density. And we use tail current density as a proxy for how many HERG1 channels are activated. So this suggests that SVP expression is increasing HERG1 channels. To our complete and utter surprise, SVP expression actually slowed the time course of deactivation. Right, yes, right. Exactly. So we also reported I also reported IPR in control cardiomyocytes that were either expressing GP or SVP as well. And again, to our complete and utter surprise, we saw that the antibody had no effect on steady state current density or tail current density or the time course of deactivation. When we got these data, we were really perplexed and confused as to what was going on. But there's a couple of things that we had to consider. One, we're using lentiviral expression, integrating this SVP into the genome for long-term sleep expression. This is also the first time we tested this in a JLN background. So although it's not what we expected, the SVP was still increasing IPR current, which is what we wanted, and therefore we predicted that it should still have the antiarrhythmic effect in JLN. So I just want to highlight, kind of put all of the data together to highlight some important differences between the groups. So I already mentioned we saw no effect on steady state or tail in the control lines. JLN current density, just expressing the DFB control, is almost more than half the current density of the control line. So that kind of mirrors what we saw with the immunostaining as well, what has been published or suggested in previous publications. And then when we express SCFE, it seems that it's restoring current density to levels that are comparable to what we observed in the control line, which is pretty good. And so then we reported action potentials from the cells expressing either SCFE or GP. I placed cells at 1 Hertz and took the average of 26 effective action potentials per cell, which is what's plotted here. And then I also looked at the variability within a set of 20 case traces, which is shown here. And you can see here that SCFE does significantly shorten the action potential duration and also significantly reduces the variability of these action potentials, which are the co-markers of PEA. We also counted the incidence of EAVs or early active depolarizations, which is illustrated here. So the phase 2 EAV is essentially an EAV that occurs during phase 2 of the action potential, and phase 3 EAV occurs at phase 3. And so you can see here that the majority of GFP expressing cells had an arrhythmic profile with showing some sort of PED, whereas the majority of cells expressing SCFE had a non-arrhythmic phenotype. So then we asked the question, since we saw that this SCFE was indeed increasing IPR, but slowing the time course of deactivation, could it be acting by increasing HERG1A expression at the mechanism? We also saw that increase in cell current density. So we took confocal images of JLN cardiomyocytes that were either expressing GFP or SCFE, immunolabeled for either HERG1A or HERG1B, and then quantified the fluorescence intensity. And so we saw that SCFE did significantly increase the fluorescence signal for HERG1A, while also significantly reducing the fluorescence signal for HERG1B. And so this could explain why we're seeing that following deactivation, although we're seeing an increase in cell current density. And so this is our data support, our working model here, which is showing that SCFE still targets the plasmamine and disrupts its interaction with the C-terminal CADH domain, but it acts by increasing HERG1 density in the surface membrane, specifically HERG1A, which is why we see that form of deactivation. But ultimately still has the desired effect of AP shortening, reducing variability, and fewer incidents of EAs. So now I'm going to move into my second project. Dave mentioned was published at the start of the year, where we looked at how differences in HERG1 segment composition mediate IPR sensitivity to protocol. So extracellular acidosis is known to disrupt cardiac function. It's implicated in sudden infant death syndrome, as well as ischemic heart disease. And there are a number of HERG1 mutations that have also been identified in certain treatments. And so we know that acidosis blocks HERG1 channel, reduces IPR current, but it also does it in a subunit specific way, in which acidosis has a greater inhibitory effect on the HERG1B subunit. And so one of the questions we asked in this project was, is subunit abundance dynamically regulated during maturation process? So to answer this question, we used an in vitro model for cardiomyocyte maturation that was developed by Todd Heron's group here at Michigan's campus. And essentially what they do is culture cells on either glass to keep them in a mature state, or culture them on polydimethylsiloxane or PDMS to keep them in a mature state. And some of the markers of maturation include mature cells typically have a lower resting memory potential, they're typically larger in size, they're finely created, and they express currents that are typically not found in mature cells, like IK1 and sodium currents. So they cultured these cells for us, and then we receive the cells and then record action potentials and IK both groups. And so first, we wanted to make sure that we could reproduce the findings that they had shown in their initial characterization paper. So we found, as expected, that matured cardiomyocytes had a lower resting membrane potential compared to immature cardiomyocytes. as well as the larger AE, and which suggests that, okay, the model of maturation is working in our hand, and we're seeing the same results that we did. So then we went on to record IKR density from either group, and here I'm showing sample traces from either immature or matured cardiomyocytes in the protocol. And we saw that there was a trend for the increase in steady state current density for matured cells, although not statistically significant. But for TIL current density, we did indeed see that matured cells had significantly larger current density. And so we went back to this question of, could HERG1 subunit abundance be changing during this maturation process? So we again took confocal images of cells cultured on glass, immature cells for PDMS, matured cells, and labeled for either HERG1A or HERG1B, and quantified the mean fluorescence density. And we saw that matured cells showed elevated levels of HERG1A, whereas immature cells showed elevated levels of HERG1B, so essentially the converse. Mature cells showed a reduction in 1B, and immature cells showed an increase in we were curious to see, do the changes we're seeing at the protein level translate at the transcriptional level? And so we did QRT-PCR again to look at transcript expression of either subunit, and found that in matured cells, they follow the same profiles, protein expression where HERG1A levels will increase, HERG1B levels reduce, and vice versa for the immature cells. 1B levels were increased and 1A levels decreased. So given these data, we see that immature cells have less current density to begin with, and they also have elevated levels of 1B. And I mentioned earlier that it's been well established that acidosis has a greater inhibitory effect on the HERG1B subunit. So we hypothesized that acidosis should therefore have a greater inhibitory effect on immature cardiomyocytes because they're expressing more of the HERG1B subunit. So we're back into the lab, did the exact same experiment, but this time I recorded IKR at neutral pH as well as an acidic pH at 6.3. And so these are sample traces of immature to matured cardiomyocytes that were reported at 7.4, 6.3. We wanted to confirm that we saw an acceleration in the time for deactivation because it's well established that acidosis drastically accelerates gating in HERG channels. So this is just the zoom in, the incidence is the zoom in of the tail current where we measure the time for deactivation. And you can see here from 7.4 to 6.3 in both groups is significantly faster. That's quantified here to the right as well. So great, we have our working model, acidosis is working. Let's see how this is impacting IKR. So we first analyzed steady state current, and I'll point your attention to the lines in blue here. So these are recordings that were done at either 7.4 or the dashed lines were done at 6.3 and 50. So as expected, we see this reduction in current density. We see the same trend from matured cells and blue. So recordings at 7.4 and recordings at 7.3. And interestingly, we see that acidosis has a greater inhibitory effect on the immature cells as we expected. So that's comparing the dashed line here to the dashed line here. You can see a greater reduction in steady state. We saw that acidosis did reduce current density for both matured and immature cells, but we did not observe that greater reduction in current density at acidic pH in the immature cells. So given these data, we thought, okay, how can we really be sure that the changes we're seeing are really driven by changes in subunit expression? So if you remember, I mentioned beginning of my talk that we can express the PAS domain and ultimately associate 1B subunits and convert them into 1A channels. And so given that we're seeing a greater inhibitory effect in the immature cells that have elevated levels of 1B, we should be able to express the PAS domain in these immature cells, convert them to 1A channels such that we should reduce the magnitude of block at the pH. I'll let that say. So first we need to validate that PAS is working. So we had an adenovirus to express paths that we got from Matt Trudeau's lab, which has a CFP tag. And we recorded steady state current normalized to the maximum cell current as a measure of rectification, which is essentially illustrated here, where as you step to more positive potentials, her current is ultimately suppressed due to stabilized inactivation. So we know that expression of paths stabilizes inactivation and enhances rectification, so that's what we're measuring here. So we see at 7.4 and 6.3, the orange lines are indicative of paths expression, and then the blue lines are GFP transducer control from immature cardiomyocytes, and you can see that paths is indeed enhancing rectification. So okay, our transduction is efficient, it's having the intended effects. Let's see how this impacts IPR next week. So again, I'm showing now examples of just recordings from immature cardiomyocytes at 7.4 or 6.3 in the dashed lines, and the orange lines are cardiomyocytes that are transduced to paths, blue transduced to GFP or control. And you can see here that again, acidosis is producing current magnitude, but in the presence of paths expression, we see that the magnitude of block is significantly reduced. Again, supporting that subunit abundance really is a driving factor for modulating IPR sensitivity to protocol R. We did also observe the same effect in tail current density, again, where low pH reduced current density in both groups, but there was less reduction in the group that was expressing the paths regime. And so to summarize what I've shown thus far, we see that immature cardiomyocytes have less IPR density. They also have elevated levels of HERG1B, mRNA, and protein. And immature cardiomyocytes are more sensitive to proton block as a consequence of this elevated level of HERG1B, which can be offset by paths expression. And so we have a hypothesis for what clinical role shifts in HERG1 subunit abundance might play. So in sudden infant death syndrome, which there's one hypothesis that respiratory acidosis may play a role in the auspices. And it's possible that perhaps HERG1B might be elevated in the infant heart. And in that case, respiratory acidosis would have a greater inhibitory effect because of the elevated level on the 1B subunit. So could that ultimately be a trigger for enhanced HERG1 block that ultimately results in QT prolongation, increasing the risk for arrhythmia, as well as sudden cardiac death? So with that, I have a lot of minutes. I want to thank my lab, of course. I could not have done this work without any of the people in the group. Adulasha, who literally took all of the confocal images and helped with the analysis, and our undergrads. Eric, who was my co-first author on our JBC paper, who always answered my endless questions. Diamond for always helping me take some pictures in the lab, and same with me while we were attaching, and same with Francisco. It's just been a great source of support during this time. And you know, Dave, do that right. I have some slides for you. I want to thank my thesis committee. When I was thinking about types of books I wanted to read, it's really important to me to have diverse representation. Too oftentimes I walk into meetings of a person of color or a woman. So I really was thoughtful about requesting leaders in the field who also belong to underrepresented groups to help me along through this process, and such tremendous support, and have gently and sometimes strongly pushed me to be the best scientist that I can be. I want to thank, of course, my funding sources, our collaborators at Tim Camp's lab, University of Porto, Cardiovascular Regeneration Core Director Core, 646 directors across the years have been just instrumental in helping me to get to a point where I could really deliver stronger presentations. Jenkins Lab, Paul, for always coming down and talking to me about anything you can think of. I will really miss our conversations, but I'll be back, so more to come. I want to thank Emily for helping me with my statistical analyses, and Carol Parent's lab, which is always going to be another lab. I have to thank Lisa Garber, Donna Shelock, and Liz Oxford, who have just been so the greatest sources of support for this program. Lisa was the one who I met and said, I know I want to do my PhD in biochemistry. She's like, what are you interested in? And I explained to her, she said, that's pharmacology. I was like, no. It's biochemistry. This is my undergrad in, I'm positive. She's like, no, I think it's pharmacology. I was like, no, I really don't think so. So she is the one who introduced me to the department first at Michigan, because I certainly would not have been this way. It has taken me a decade to get to this point. I have to thank my advisors at Georgia Tech, Dr. Carrie Scheffler, Dr. Lazari, Dr. Lieberman. I applied to grad school in the fall of 2012 with a 2.6 GPA, no research experience, and I applied to like Hopkins, Georgetown, reach for the stars. I did not get in. I applied to postbacks, I applied to master's programs, and these three people really helped me to create my own plan and support me to build the research skills that I needed to become a competitive applicant and to thrive in these spaces. And the techniques I've learned from Dr. Lieberman have helped me throughout my career, and still techniques that I use to this day. So thank you for helping me get here. When I finished working as a research technician in Dr. Lieberman's lab, I applied to this program and was not admitted. And I didn't really know what the plan was from that point, but I have to shout out MCD Bridges program here in Michigan, because they recruited me to apply to their master's program. It was fully funded, it had health insurance and benefits, and was really designed to serve as a bridge into the PhD program. And that is the reason why I'm still here at Michigan. And I have to thank the Chapman Lab and Matt and Maggie and Janet and everyone who's in the audience. My plan was to collect this master's and leave. I never put that in my application, but Matt has been one of the most supportive advisors. Whatever I'm sharing across the board. So I'm just so grateful to your support and mentoring through this process. And Maggie is like, one of the coldest scientists I know. Somebody that I look up to, and I have 5 minutes. So then I took a gap year in Fulbright, and I have to shout out Jean-Francois, who I met through Matt in their lab, my lab mates. They were the perfect example of brilliant scientists who had a healthy work-life balance that I clutched to during this program. They took long lunch breaks, they didn't come to lab on the weekends unless they needed to, they didn't stay too late, they didn't come too early, and we still published some of the most high impact journals in the world. Being that tangible example, let me know there are many ways to show up and do science. I'm gonna shout out Fulbright Mar. I think Eric is on the call from DC or Belgium. Thank you all. Okay, so to Michigan. I made these slides in 2019 when I told Matt that I was gonna join these slides. So I'm gonna give you all, you gotta read fast because I have 3 minutes. Anthony is from Canada. So then I joined this lab. And the first order of business Dave did was flood the lab twice. And the first thing he said was, "Oh, please don't tell Paul." I was like, "Of course." And immediately went and told Paul. Shout out to Diamond as a witness and for sending these pictures for love away. I feel so honored and blessed to have been a part of your lab. If I could do it all over again, I would choose your lab, not knowing what EFIS was, not knowing how to patch, being your first student in that. Honestly, one of the best experiences of my life. You've pushed me to be a better scientist. We've had a lot of discussions that have pushed me to be a stronger advocate for myself. And I'm really just grateful for your support as someone who genuinely cares about us as people. And I know that you have shown up every day and given your best importance to us. So I don't always share that or express that on Twitter, but I have to thank my EFIS family across all over, Dave's kids and Charlie and Elise, my Black and Biophysics team, my lab again. Oh gosh, and my friend, to the enjoyment crew, to Kwaku, Adeze, Ramona, Joy, Vanessa, I'm naming everybody, Nat, Alexandria, Francine, Jen, Viola, Dom, Janet, Maggie, Io, Lydia, y'all have been, oh my gosh, just such a vital source of support during some of the most challenging times of my life. I can shout out Warren and Brittany, Jade, who sent me Uber Eats when I was not finding time to eat, Brando, who's here all the way from Chicago, Corey showed up for me during some of the toughest periods of my life. Sierra, Nami, who's continued to mentor me from the beginning through to the end. Literally last week when I was stressing about my defense. Encounter my sister, Omega, Ijoma, Nicole, and Shana, who are all like everybody on the side is like family to me. Love you. And I made it. And I hope that you're here with us. And to my mom and my sister. Being here. Thanks today. It's like a 0.1% chance that I want to have children, but if I do, they have to have a sibling because I have been so blessed to have a sister. Dr. Victoria, first in the family to go to college, her Ph.D. in organic chemistry at Georgia Tech in 1984. She is the blueprint, my model, my inspiration. I am so incredibly blessed to have had someone to call upon during this process. Thank you for guiding me, for helping me, for supporting me, and uplifting me through it all. In and out. You could shoot me. Thank you. And I have to thank those who came before me, Edward A. Boucher, who was the first Black person to receive a Ph.D. in an American University Honor Society. I'm so honored to be a part of, and the first 3 Black men to integrate Georgia Tech in 1961. I'm so grateful to those who have come before me to pave the way, and I hope that I have made a space and made it easier for those who come after me. And I have to thank everyone who has given me a hug, not knowing I needed it the most, who's prayed for me. Helped me change a tire when I got a flat at MSRB at midnight, was ready to quit. I'm done. This is it. I just appreciate all of you so much throughout this journey. So thank you for being here today. Thank you for your support. And I really appreciate it for that.
I got an easy one.
Yes.
So, and I feel that after all those years of work and all the efforts, all of those beautiful words you had for the scientists around you, it's fair to, you get to shine and tell us your thoughts about your data, right? Like you've been working on this a long time, but my question is super simple. So the acidosis, I just know nothing about range of pH. So that manipulation, is that like a real extreme, or is that a level you would actually see with acidosis in a person or infant?
Yeah, no, that's a great question. I will say I'm not aware of any data that has been able to record and say like pH levels in an infant due to the acidosis, but that's more of a technical issue, like being able to get, you know, those kind of patients. I would say that 6.3 is definitely an extreme. It can occur, but I think if you drop a couple of 0.3, 0.5 units, even that is gonna have lethal consequences. In a person. So 6.3 in a person is extreme, but still something that could occur.
Thank you.
Great talk. You mentioned the changes in isoform expression during development. Is it known whether that change in isoform development is uniform in nature, or is it non-uniform, is all cells at once, or parts of the heart at once? Does that?
That's a good question. So I think the only data, not overspeak, but there's a study that has looked at specifically HER1A and HER1B mRNA levels in human cardiac tissue. That's really the extent to which the data has been published on that end. So we can't even entirely say that the protein is necessarily shooting at that point. I would guess that the change is probably dynamic. We don't know what the stoichiometry of these heteromeric channels are to begin with. So, I mean, I think it would depend on the system, but my guess would be that it's probably, I would say it's changing throughout different tissue at different time, depending on the needs. Yes.
On the isoforms, do you know, are those present in other species, besides humans, that are A and B?
Yeah. So, I don't want to overstate it, say all of them, but for sure, and mice, rabbit, dog, guinea pigs. So yeah, they do, the other HER1 components do exist.
And I guess those ratios would change depending on the species.
They do. So actually, in mice, you actually see the opposite trend where the immature myocardium shows elevated levels of 1A as opposed and mature show elevated levels of 1B, inverted and most in human cardiac tissue.
I'm really interested in the non-specific specific peptides.
Yeah.
Do they then have a different effect if you were homomeric or heteromeric for the PAS domain there?
Oh, that's a good question. So the small, okay, so the selective, non-selective small molecules, they typically tend to bind within the core region of the PAS domain, which is consistent between both 1A and 1B. So they should still interact with the channel. But their effects, I would think, might differ based on relative abundance of the PAS domain, since the heteromeric and homomeric channel have different functional properties. But as far as how the molecules interact, I would expect that to be comparable. For the SCFV that we used in the paper we're writing, that is selectively designed to target the end community, so shouldn't have any impact on the community. Yeah. Can I guess finally?
Congratulations. Yeah, exactly.
My new last I saw you now. Enjoyment. Amazing. Yeah, we call her doctor. I'm just gonna and then just. Yeah. Back this is right. Can I ask y'all to leave? I have to do my close door defense with my committee. But thank you all for coming. Thank you for coming, Jean-Francois. Tell them my bicycle. Love y'all.